The Uart receiver is the component that implements the oversampling scheme that the Uart protocol actually depends on. Exactly what it does, it monitors the RX line in here, which is just a single wire, and it does the oversampling on it based on some ticks that come from the baud rate generator out there in here. And every single time it reaches the middle point for either a data bit, a start bit, stop bit, or even a parity bit, it just basically samples it and shifts it internally into one of its registers, which basically just it's a finite state machine with some sort of a shift register. Once it actually shifts some data bits in here, how many bits you have, you issue the R done tick in here, and you basically make it available at its output, and it can be written into the FIFO if we choose to. So how is it constructed? Well, in its most simple form, again, it's a finite state machine, and this particular finite ASM chart here tells me that this finite state machine has a few states, exactly four. I have an idle state, start state, data state, and stop state. And as the name actually imply, the idle tells me it's an idle, start actually is the start bit, data is actually all the data bits, and stop, and probably, I'm not showing parity bit in here, but probably I would have included it in here, and I have the stop bit in here. So what does the idle do? Well, the idle actually does the following. It keeps monitoring at exactly the tick. So everything you see in here, it moves it exactly when the tick happens. Okay, so I'm looking for, most likely I'm looking for the ticks, but not for the idle, sorry. So in the idle, I'm monitoring the RX line. Once it actually goes to 0, because remember at idle it's 1, when it gets to 0, I'm actually going in here and I'm starting something, I'm making S equals 0. And S is just basically a counter. Okay, and that counter, I counted it at 0 so that I know how many bits are there. So then we move to the start, and this is basically the state that implements the start bit. What it does is actually tell me, is it an S tick? If it's not, I'm going to stay in here. And if it's not S tick, it's actually here. So what does the S do? The one that we did the 0, it actually compute how many of the baud rate ticks happened. And once I reach 7, if you guys remember, we reached 7 in the very start, basically the start bit. I'm going to actually reset it one more time. And I'm going to reset n, and n is actually the number of data bits that I have, which currently at this point I don't read any, so I'm going to set it to 0 and so forth. So if you read it, it's actually, as long as it's not 7, it's actually going to increment it. Once it actually reaches 7, that's it. We're going to put it at 0, and then we're going to start, and we're going to go and receive the data bits. And in the data bits, I'm going to only move when the S tick happens. So when it's actually happening, I'm just going to keep doing it till I reach 15. And when I reach the number 15, that means I'm in the middle of that data bit. So I'm going to sample it in here, and of course I'm going to reset that particular ticker, basically how many ticks happens, like 15 or 16 and whatnot. And this here just tells me that it's basically a shift register, and I'm just ordering it with the received bit. So I'm going to shift an OR, and that's how I'm going to do it. And of course I will have to stay in this data bit in here as long as I'm actually reading the data bits. So it depends on how many D bits, and if you remember, D bits is actually a parameter that tells me how many data bits I have. If I have a parity bit, I would have probably put it in here. So once I receive all data bits, let's assume that they're 8. This is the default value we're going to implement. It's 8. You actually move to the stop state, and the stop state it's exactly the same. You put the in here somewhere. You actually put S equals 0. Then you weigh when S equals SB tick. Remember, the SB tick depends how many ticks happens for the stop bit. So if I want it to be exactly 1, and that means I'm actually waiting for the S tick to be 60 minus 1, which is 15. If I wanted something else, I'll like maybe a bit and a half for the stop bit. I'll actually add half a bit, which is 8 in here, and I believe that will become 24 ticks, for example. And if I wanted 2 bits stop bits, I'll just basically that number, I'll put it to 32 and whatnot. But anyway, and here in the FSM is just basically implementing that. And of course, during that period of time, the RX, I believe it should be basically done after it's done. After it's done, like reading all these SP. After it's done, it just basically issues 1 clock. This is exactly for 1 clock cycle, and goes back to the idle state. So how is the code implemented? It actually follows the graph line by line. Basically, it's exactly the same. It's an FSM. We call it an FSMD, which is basically an FSM with some data paths, because it has some data it's manipulating. But if you follow it, it's actually a case statement. I have an idle, a start, and a data, and a stop, and it's following that particular graph exactly